Yeah, okay, so the aim of this presentation will be to give a brief introduction to what Namada is, as well as a brief introduction to private bridges. So to start off, what is Namada? Well, Namada is the first fractal instance built on the Anoma architecture. So if you're listening to Adrian's talk earlier, that's what Anoma is, and to learn more about it, I would highly recommend reading the white papers that we're distributing by the entrance. But for the purpose of this presentation, you can think of Namada as a privacy for assets focused blockchain. So to start this presentation, I'd like to motivate why we care so much about privacy. Well, first, I like to think about it, why am I so into cryptocurrency? Why am I here? And the idea is that I want to be able to transact in the presence of adversaries. The problem with transparent blockchains is that I have to trust that not a single party in the entire world that is watching the blockchain will use the data that I emit for my transactions in a way that I don't want them to. And that creates a N out of N trust model, which I generally would not like to operate under. So I come from a machine learning background, and by now I'm pretty confident when I say that your everyday transactions leak a lot of data about you. That's why we have all of these loyalty programs where companies pay you in order to reveal your data to them. And as Target, the American company, showed recently, is that they could use your everyday transaction data to predict if you're pregnant even before anyone in your family knows about it. So that brings us to the first user feature of Namada, which is the multi-asset shielded pool, which will help you keep all of this information private and only to yourself, and then reveal it to who you want to reveal it to. So at a very high level, how this works is that using some really cool cryptography and zero-knowledge proofs, Alice is able to transact freely while still being able to hide what assets she's transacting with, how much of this asset she's transacting, and with whom she is transacting with. And in addition to this, we also have the ability for Alice to have the discretion to reveal exactly what subset of this information that she wants to reveal, and also to what subset of people that she wants to reveal it to. So a very relevant use case of something like this is perhaps what you want to be revealing to the OFAC board to prove that you're not interacting with any sanctioned addresses. But because this is built on the Anoma infrastructure, we can also have things on our validity predicate that prevents us entirely from transacting with sanctioned addresses, and that's all that we need to show to show that we're being law-abiding citizens. So we also believe in Anoma that we should be subsidizing public goods. And why do we believe this? And I like to think about public goods, I like to think about privacy as having this positive externality, because a privacy set is essentially useful as a function of how many users are already in it. So if we start off with Namada having 0 users, and you bridge your assets over, then this is not a private blockchain, right? Because you're the only user using it. And we could end up in this inoptimal equilibrium to the left, where before we reach a threshold, a critical threshold of users, no one will want to enter the blockchain. So if we could construct this subsidy schedule whereby at any level we have the benefit being higher than the cost for entering this privacy set, we can guarantee that we always reach the optimal equilibrium with the maximal user surplus. And I would also like to argue that we could make this subsidy schedule finite ad infinity. So to read more about that, I will soon release a blog post on that. So finally, we need to be able to implement this in a way that still preserves privacy. And the way we do that at Namada is through what we call a convert circuit. And the details is a bit out of scope for this presentation, but please come talk to me after this talk. But what happens is that by holding assets on Namada, you accrue like subsidized NAM tokens over time that still remains anonymous, and once you withdraw or someone you've transacted with withdraws this asset, you receive your rewards in form of NAM tokens. So, but the road to public goods doesn't just end there, because we believe that there is this idea of, if we want people to bridge over their assets to Namada, there's this problem that if this is done transparently, we have independent privacy sets between every single bridge to Namada. And that creates unnecessary competition between bridges, because essentially in order to get the maximal privacy set, everyone needs to go through the same bridge. However, if we can implement private bridges, we circumvent that entirely. And that's when I pass over the mic to Iraklis, who gives more details on how that will work.
Hello. So, apologies first, my slides have some math. So, I guess I don't need to motivate you why we need bridges that much, but for those of you who need some motivation, so imagine you have your star token and you want to convert it to a circle token, and you have to go through some exchange platforms, and those exchange platforms, they are not interoperable, so you convert your original star token to some fiat currency, and then from fiat currency you go to the circle token, so that imposes a lot of fees and is way more complicated, is expensive and slow. So what is a bridge? It's an entire protocol. It can be a toolkit. At some point, it's a smart contract. It's a special vault account. It's some relay, layer and light nodes logic, which has been incorporated in order to transit the state between the two blockchains. There's a lot of validator logic, and there's an entire orchestration of all of those. So the architecture on bridges looks like that. We have our source chain A, and you have your target chain B. You have a different set of validators, and you want to convert X star tokens for Y circle tokens. So first of all, custodian bridges, we don't like that much because there's a lot of centralization and there's a lot of privacy exposure. So you give away all of your tokens amounts to some third parties, and we don't obviously like that. So trustless private bridges, they on a high level look like that. You don't only have privacy individually on each source chain. That being said, if you're familiar with Zika style, we don't only need to keep in private the amount of transactions, the target and the source, like we do in the snarks of Zikas, but we want also privacy on the bridge itself. So the bunch amount of transactions that are being held from bridge A to bridge B, we need to keep it in private. So the requirements, we need privacy at each bridge. We want private common state. We want simplicity, speed, and of course a lot of security. So I guess the majority here is familiar with the flow of IBC-style cross-chain transactions. So you have blockchain A, blockchain B. You instantiate some transactions on your source blockchain. This has been monitored by some validators, and then equivalent amount of tokens are being minted into the target blockchain. And then there is some sort of voucher which authorizes to the wallet of the user the minting tokens on the target blockchain. So what we've seen so far that is missing from the exchanging bridges in the private sense is that when some crash is happening on the target chain, for example, either due to adversarial behaviors or due to some network crashes, and ideally when the source chain A is asking to revert back all the transactions that have been going through the bridge, we don't want to reveal that amount of transaction that happened. We want everything to be in private. So in order to solve that, we need some sort of counters to hold all the amount of transactions that have been held from blockchain A to blockchain B in a private way. That means they're somehow homomorphically encrypted without actually ever being decrypted at all, the total amount of transactions. And then when there's a crash and you want to revert back, we have some comparisons which also happen in a private way. That being said, that the total amounts are also can be private, but you can learn the result of the comparison. So that is part of our solution. As I said, we use some private counters for our protocol, and we achieve this fault isolation with some secret computing modules, which I'm going to show you right now. So in secret computing, very generic architecture, you have a function f that you want to compute. There are some private inputs, x1, xn, and you have some either private or public output. So f is public, inputs remain private, and the executor, using some secret computing technology, it can learn y without actually touching at all the x's. So if f is a linear combination, some technology that is called multipolic computation can provide some very viable and efficient solution to the problem. So on a high level, suppose that you have those 4 minions, and they have some integer values that they want to keep private, and they want to compute some aggregate functions like the sum. So the way the protocol works, like at the first phase, you can see that the yellow minion is secret sharing its value to the other parties. That being said, when you add all of those values, it adds up to the original value, but if there are no collisions at all, none of the minions understand anything about your input values. So all the other parties compute their values subsequently, and it's not hard to see that if you add all those values, then you end up with the correct sum in private way. So you never reveal your original value. That is for additions, but to do some more involved computation which involve multiplication, you need some more, more logic into your protocol, and you need some sort of structured randomness which has been distributed into the parties in order to compute additive shares of the multiplication. So the idea is that you have either a set of parties or a trusted party who distributes the special randomness, and then the parties, they run that circuit, and if you follow in a personal paper, you can see that in the end of the protocols, what the parties are holding is actually additive shares of the multiplication circuit. So by doing, in a privacy manner, additions and multiplications, you can build almost anything you want. Actually, we don't have a lot of time to show you how comparison will work in that fashion, but this is the basic idea. So to recap what we've seen, so explicit cross-chain transactions are expensive. Bridges protocols provide a toolkit for cross-chain transactions we can say in one shot. We don't like custodian bridges because they give away too much privacy. And we augment and we improve our existing private bridges technology with fault isolation. And we strongly believe with multi-party computation, due to the fact that the entire nature of the protocol is in a multi-party way, in the sense that you have multiple validators being connected, can provide a viable solution to the problem of private bridges. Thank you very much.